Quite a marathon. So our fifth talk of the session is on scalable and robust global load balancing. And our speaker is from ByteDance. Shankar is a network software engineer at ByteDance, and he focuses on research and design for Ethernet switches and network operating systems. Shan, please.
Hi, good morning, everyone. My name is Yushan Kao. Today, I'm going to present the SGLB Scalable and Robust Global Load Balancing in Commodity AI Cluster, a joint work by ByteDance, Peking University, Shanghai Jiao Tong, and Broadcom. So firstly, let's go through the background and motivation of our research. It's well known that AI training traffic has the following two properties, low entropy and burstiness. So the first property, low entropy, is caused by the data parallelism, pipeline parallelism, and tensor parallelism commonly applied in AI training. The parallel process communicate mainly within the assigned parallel groups, causing the number of flows to be relatively small compared to the traditional data center networks. And the second property is burstiness. So AI training algorithm from the GPU's perspective are iterative, flipping between gradient computation and model update. Parallel processes swing between computing and communication periodically and simultaneously, causing the network traffic to appear all at the same time. So other than the two properties, there's a challenge commonly observed in the AI training cluster, which is link failure. As pointed out by SIGCOMM'25 paper, Alibaba, HPN, 5K to 60K link failures per day were observed in their production AI training cluster. Packet loss will cause packet retransmission, which exacerbates the long tail effects and slows down the overall AI training process. So our goal is to design a good load balancing scheme that leverages the large number of paths in the cluster to provide a high peak throughput and at the same time adaptively reacts to the link failures promptly. So this slide shows our intuition about the global and adaptive load balancing scheme. So as you can see in the picture, when the bottom left S00 is sending a packet to the bottom right S02, with the traditional commodity Ethernet switch, ECMP is usually applied so that S00 would choose an output port based on the packet's 5-tuple hash results to send the packet to S02. ECMP is oblivious about the current queuing status, so that there's a chance for S00 to choose the worst route, BY in this case, for the packet to go. The intuition is that S00 should be aware of its local and remote queuing status and pick the path with the best traffic condition for the packet to go. In this case, the path CZ has the most empty queues, so it should be picked by S00 to send the packet. So luckily, the state-of-the-art Ethernet switches provide the capability to exchange the GLB messages periodically on a scale of microseconds. As you can see in the left-hand side of the picture, a GLB message contains the queue length and link status of every port. Combining the local and remote information, S00 in our previous example can make the optimal choice when picking a path for the outgoing packet. So with advanced switch ASIC supporting GLB messages available, there are three major challenges when we're designing the system. The first challenge is that we need to build a control plane to work with the ASIC's ability to send and receive GLB messages. The second challenge is coming from the switch ASIC resource limitation. In other words, a chip can only store a limited number of path qualities, and numbers could be far less than the complete set of paths from a switch's point of view. And the third challenge is to design the fast link of failure handling scheme without impeding the existing routing functions running on the NOS and the switch ASIC. So before we jump into the design to address the challenges, let's go through the target system. As you can see in the picture, this is a typical AI training cluster containing around 10K GPUs and almost 1,000 64 by 800 gig Ethernet switches. There's a 3-layer class network with 256 switches in each layer. A blue box is called a rail, containing 32 by 32 fully connected Tor switches and spine switches. A green box is called a plane, containing 32 spine switches. From a leaf switches perspective, taking L00, for example, it is connected to all the SPI switches within plane 0. For instance, for L031, it is connected to all the SPI switches within plane 7. From a SPI switches perspective, take S00, for example. It has 32 egress ports facing down and 4 ports facing each rail. That is, S00 is connected to 4 different leaf switches in any rail. So this slide shows our design to bring the control plane and data plane to work together. As you can see in the picture, there are 3 major components highlighted by the red labels: the network OS, the switch ASIC, and the embedded processor provided by the switch ASIC. So during runtime in the control plane, BGP is responsible to fill in the path group and the path values in the 2 ASIC forwarding tables. And sync mesh, on the other hand, is responsible to communicate with other sync mesh residing in other switches to acquire the topology information, and translate the switch ID and port ID within the GLB messages into the group ID and path ID in the ASIC table, so that later GLB engine can fill in the quality values in the right position. So GLB engine, as I just mentioned, is responsible for filling in the quality values carried by the GLB messages in the right position of the path quality table. So during runtime, data plane, when receiving a packet, the data plane will look at the packet's destination TOR and find out which group it belongs to and choose a path within the group with the best quality value. So here we discuss the path quality table scalability issue. The problem is caused by the limitation that a typical Ethernet switch provides roughly 2K path quality table entries. So from a T00's perspective, the number of path qualities for the intra-rail TORs is 32 leaf by 31 TOR, which is 992. But the number of path qualities for the inter-rail TORs is 32 leaf by 32 SPI by 4 leaf by 224 TOR switches. And the number will be 970K, and 917K is almost 500 times larger than the size of the path quality table provided by the switch ASIC, which is 2K. So 970K is much larger than 2K in this case. So then we come up with 2 designs to compress the path qualities. The first solution is that from a switch perspective, it only cares about the path qualities within 3 hops. And the second solution is that a source TOR only cares about the path quality when the destination TOR is within the same rail. And our argument or our intuition is like looking too far and looking too early doesn't really help improve the load balancing quality, since the path quality from 4 hops away may very likely be outdated when traversing many hops to come to the source switch. Besides, by looking at only 3 hop segment quality, the GLB message only needs to be exchanged between immediate neighbors, and this reduces the amount of GLB message aggressively. So similarly, from a leaf switch's perspective, if it has to record all the possible paths to every different TOR switches, the total number of paths will be 28K, which is about 15 times larger than the ASIC path quality table. By only looking at the path qualities to other leaf switches that are 3 hops away, instead of to all the TOR switches, the total number of paths can be reduced to 896, which is far less than the 2K limit. So now we look at another challenge, fast link failure handling. As you can see in the picture, when link down happens, the goal is to remove the associated path from the path quality table. So traditionally, the network always relies on BGP to for route convergence when link failure happens. The problem is that the BGP takes too long for route convergence. As you can see in the picture, a link failure between S70 and L731 will cause 32 by 7, which is 2 to 4 BGP messages to come to T731 before the ASIC routing tables can be updated. So SGLB, on the other hand, uses just 1 message to propagate the link status to the immediate neighbors. Below are the steps for switch to handle the link failure. First, the GLB message has to arrive to the GLB engine. And second, the GLB engine uses a callback function to inform the orchestrator about the link down event. And third, orchestrator consolidates the routing events from the GLB engine and BGP to avoid a potential race condition. And finally, orchestrator used the customized API to update the path quality table in the ASIC. So next, we come to the evaluation part. In terms of code implementation, there are roughly 15K lines of code implemented in Golang and C++, written for sync mesh orchestrator and the EDK running on the embedded processor as mentioned previously. And the testbed is a 3-tier cluster network topology with 32 GPU servers and 14 Ethernet switches as shown on the right-hand side. The baseline algorithm to compare against SGLB or ECMP and DLB. So DLB is just another load balancing scheme provided by the SOTA, which is the state-of-the-art Ethernet switches. The difference between DLB and GLB is that the DLB only look at the local queuing status instead of the global queuing status. And the workload being tested is Nico test with all-to-all and all-reduced collectives. The simulation platform is constructed by Chakra, AstraSim, and HTSim. In the simulation, the topology is larger, containing 256 GPUs and 4 rails, 4 planes, each containing 8 switches. The baseline algorithm to compare are ECMP, DLB, Drill, Hedera, Conweave, Conga, and NDP. The descriptions of each algorithm can be found in the paper, so we're not going to address the details here. The workload being tested is all-to-all. Now we look at the testbed performance. For either one of the collectives, we conducted 2 types of tests, one without background traffic and the other one with background traffic. The background traffic is essentially a 400 gig leaf to Tor flow and another 500 gig Tor to leaf flow. As you can see on the top right, without background traffic, SGLB has a slight 3.8% performance advantage over ECMP, and with background traffic, SGLB has a 60% performance advantage over ECMP and 15% performance advantage over DLB. Regarding all-reduced test results in the bottom right, we tune the background traffic volume in the x-axis, and as you can see, SGLB's GPU bus bandwidth is never affected. This is because the total all-reduced bandwidth requirement is far less than the bisection bandwidth provided by the topology. So next, this slide shows the simulation results. In the bottom 3 picture, we show each algorithm's performance under different message size. And the message size range from 64 meg, 256 meg to 1 GB. And in the top right pictures, we show each algorithm's performance under different topology sizes. As you can see that SGLB constantly outperforms other algorithms independently from whether there's background traffic, the message size, and the topology size. So this slide compares the link failure convergence time between SGLB and BGP. As you can see from the table, BGP's link failure convergence time is over 1 second, while SGLB can achieve a sub-50 microsecond link failure convergence time in in all kinds of scenarios that were tested. So to conclude our presentation, we propose SGLB, a packet-by-packet global congestion-aware load balancing scheme to provide high peak bandwidth and a fast link failure handling for the AI training network. There are 3 major challenges to address in our work. So one, control plane, data plane co-design to unleash the ASIC capability to send and receive GLB messages. And second, a path quality compression design to scale to big O 10 to the 4 GPUs. And third, a fast link failure handling design. We also prototyped and evaluated SGLB in extensive experimental settings. And thank you very much for attending our presentation. Now I'm happy to answer any of your questions.
Any questions? Well, people think maybe I can take the first one. I have quite a few, but so you mentioned it takes 50 microseconds to learn that a path has failed and sort of to not stop using it. This has an implication that even for the load balancing, you still have some delay before the load propagates.
Yes.
So is there, you use sort of large collectives in your tests, right? So what is the threshold at which SGLB stops working so well? Like what flow sizes do you need for it to work well? Because you have to propagate, you have to have stable traffic patterns for it to work well, it seems.
Right. So the trick that we apply here, remember that I mentioned that there's a 3-segment limitation in terms of the propagation of the SGLB messages. Mm-hmm. The GLB message provided by the ASIC capability. Mm-hmm. So the switches only communicate with the immediate neighbors with the GLB messages. The GLB messages are never routed or transferred beyond one hop. So that means that if we're facing together, we're physical neighbors, I only send GLB messages to you, and after you read it, you record that in your ASIC tables and you just throw it away. So that guarantees the latency is minimized between just 2 hops. In many cases, they're just microseconds away, and the amount of the traffic hindering the production network traffic are minimized as well. Okay.
Right. Any other questions? Yeah.
Hello, I have a question about the GLB engine. Is this engine that's baked onto the hardware? And like, if we have custom packet rate strategies, and can we just like have some weight manipulations, like we custom our work? Is this GLB engine will be provided through like Broadcom switch chips, or is a ASIC work?
I can probably answer that, but we can take it offline. Any other questions?
So I have a question. Is this an experiment or is it deployed in production?
It's almost in production.
Okay.
Yeah, thanks.
Okay, great. Let's thank our speaker again.